to introduce our first speaker, who's Simon Godsall, who's based in the signal processing group here at Cambridge, and he's going to be talking about Bayesian inference and continuous time-driven processes.
Thank you very much, Paul. Right, so I'm just going to try and give a flavour of some of the change point related works that we've been doing in recent years. Some of it's old stuff, some of it's new stuff, so apologies if you've heard any of it before. Oh dear. This could scupper everything. Is it my computer? May just, perhaps if I screw this more firmly together. Okay, we'll see what happens. So applications on the left there, we're looking at inference for change points about jump positions in time series data. So those two examples are, on the left and in the middle, are financial time series, where we're looking for things like sudden changes in the trend of the process. In other words, is the price going up and then it suddenly starts going down? Or indeed, does the value suddenly jump up? Trying to distinguish that from the observation noise, which could be leading you towards a different conclusion over the short term. And we'd like to do all that sequentially. So a lot of these applications need to run in real time and sequentially. So we're trying to extract probabilistic inferences about things like the probability distribution for where change points may have occurred within the last 10 minutes or whatever. On the right, I don't know if I'll have time to get onto this material actually, but I just wanted to briefly mention it. Change points in dynamic structures of coordinated objects, for example, groups of animals or birds, and if we can have some kind of coupled dynamical model for the way that objects interact with each other, both spatially and temporally, then perhaps we can learn some latent structure about which objects are connected together in a group, and do those group structures change dynamically over time, and can we identify when those occur? And most of these problems we pose within an underlying continuous time dynamical model framework, whether it's just for a single price object, like in the case of the finance data, or whether it's for a multidimensional coordinated object that's moving both in space and time. So I guess that's probably what I've already told you. We're tending to use a continuous time formulation, and we tend to adopt the Bayesian paradigm in order to give us some kind of a model-based approach. So we'll rely on some kind of underlying model, and then we'd like to extract from that probabilities about, so give us our uncertainties about things like where change points have occurred, and how likely they are to cause structural changes in the future, and so on. So financial data are a good example of this, where, as I say, the jumps or the change points, and these two terms are used synonymously in this setting, are changes in the behavior of a price process, here an exchange rate. So we're assuming underlying this that it's not just a Brownian motion, that there is some kind of underlying trend process which drives it most of the time, but which can rapidly change. So you can have a very rapid change of fortunes, and you need to lock onto that sequentially as fast as you can. We also work in tracking problems, where if you're tracking evasive and maneuvering objects, animals, aircraft, people, they make sudden changes in their maneuver characteristics. They may appear to be doing a smooth turn, and then they suddenly change to some other more kind of erratic behavior. So we want to automatically learn online the positions where the maneuver has changed to some new parameters, and you lock onto that, and then you get better tracking performance and understanding of the scene from that. And then finally, these sort of group object problems, where you can look at coordinated objects moving around spatially and temporally, and trying to, I don't think we need to know that Jens is on Skype, do we? Let's get rid of him. No. Now what have I set off? Okay. Actually, Jens runs the audio stream at Skype, so I suppose he would be on Skype most of the time. and these group objects tracking problems. The idea being that one would like to scale up to huge problems with swarms of individuals, but computational problems persist at the moment, I think, for the very large-scale problems. Tend to model in continuous time. Observations will be discrete in all of our settings. We're not doing continuous filtering, as some people work on, but the observations can arrive at arbitrary timings and out of sequence. So it's quite convenient to put this kind of thing onto a continuous time skeleton process, because then you don't really mind when the observations arrive. You just kind of tap them in at the instant you require. We very often, the underlying dynamics of the system are often more naturally explained in continuous time as well. So if you can do it, why not? It's a more natural framework for explaining many natural and man-made behaviors. And we tend to use Bayesian Monte Carlo inference methods for solving these problems, because the models we have are usually intractable to analytic inference and so on. Okay, I won't get through all of this, I'm sure. I'm going to have to dump some slides along the way. I do apologize. But we'll talk a little bit about the continuous time stochastic models that we're using, and the Monte Carlo methods and state-space methods for inferring the hidden states of those models, the examples in finance and tracking. Am I back again? It looks as if it is that plug there. Okay, well, this gives us a natural pause in the lecture. To consider. Okay. So the example of the jump models, where the change points there are the positions of sudden changes in value or trend of a process, and I may get time to talk a little bit about the structured group tracking problems as well. And in the jump processes, I may also talk about some alpha stable modeling, where you actually say that there's an infinite number of jumps in any finite time interval. So this is some recent work that we're doing. That's a really fascinating topic that I'd hopefully like to introduce. Okay, so the kind of framework we're looking at is generally diffusion models, where you're looking at the incremental changes in some state variable x over time in terms of a drift and a diffusion coefficient, and usually some Brownian motion plugged in there. Things like continuous time autoregressions can be put into this type of framework, as well as many other models from finance and other areas. Here we're particularly looking at cases, though, where this is not Brownian motion, because we're going to have sudden changes that can't be modeled by a Gaussian component in there. So we'll need to identify where those changes. I wonder if there's something I'm doing here that's causing this problem. Have other speakers had this problem? Let's move on anyway. You think it might be my adapter? Yes, we could try that. Yeah. Is it? Yeah, okay, like the Mac. Okay. Right. Yeah. See what we have now. I've never tried it with one of these Mac adapters before, so it may not find it at all. There we go. Right. Okay, we'll give it a try. Thank you. Okay. And most of the models we'll look at will actually be in the kind of linear version of that, where this drift coefficient can be written as a linear function of the state. So that gives us some partial analytic tractability in the models, because things remain. If this thing is Gaussian, then the whole process remains Gaussian. So it's some kind of vector OU process, Ornstein-Uhlenbeck process, but we'd like to replace the W with a jump process with change points in it, or certainly a non-Gaussian heavy-tailed process that can model extreme events. And we can, in principle, integrate that up using stochastic integration. And if it is indeed Brownian motion, this W, then things are very straightforward, and we have a Gaussian transition density that can be written down straight away. But we're, as I say, interested in the non-Gaussian case modeling, the heavy-tailed and extreme events in the process. So a simple example that I give that's quite useful for some financial time series is just a stochastic trend model with some jumps in it. So you're looking at x is your state variable again, and we're looking at incremental changes in the slope of the process, the first derivative of the process over time, so that's the x dot. And we think of that as the trend process. So if you're all on an upwards trend, then you know that you can predict the future and make a profit out of that exchange rate or commodity price. But that trend process is assumed to tend to die down over time according to some kind of mean reversion to zero, so the trend doesn't continue forever. But it can also be shocked by sudden jumps in the W process. So a very simple way of modeling that is to say that W is comprised of a Brownian motion part, that's a scale Brownian motion, plus a jump process. Now this is where the change points come in, because then you've got Z of t, which is making up this W process, is comprised of a summation of discrete of random jumps occurring at random continuous times tau of k. And so you just sum up all the jumps up to time t to get the value of the jump process component up to time t. And in the simplest example, you can even take the jumps themselves, their values, not their positions, to be Gaussian distributed with a particular mean. And yes, go on.
Are you assuming independent increments and that the size of the increment is independent of the state of the system?
Yes. In this version, yes, absolutely, yes. I mean, in other finance models, one might want to introduce that dependence. So I won't consider that here for these cases. But yes, we can make quite a simple and fairly tractable model if we make those jumps Gaussian, and then pretty arbitrarily assign a transition density on the jump times, the change point arrival times tau. So these might proceed themselves according to some Markov transition density f, telling you the distribution of the next jump position given the position of the previous jump position. We're not limited to Markov transition densities. It could depend on a history of jumps and change points, but that doesn't change things very much. So for simplicity, we'll leave that as it is. So the kind of paths that you get for the process, if you have an Ornstein-Uhlenbeck process for the trend process, you can see that the change points or jumps are occurring at all of these positions where you see a sudden change in the process. Then the trend process tends to tail off towards zero, or it could tail off to some long-term trend if there's a long-term trend known to be present in the series rather than zero. And then you integrate that up and get the price process itself. Comparing that with the actual data, similar qualitative behavior, but of course there's a lot of market noise on there. So these things are all observed in noise. So the X process and the X dot process are part of the unobserved part of the system. That's just showing the same thing on a bigger scale, showing that these jump times that we want to infer sequentially occur at random positions and cause a shock to the system in terms of the trend process going up or down by some random amount. We could do similar things in, I'll show some brief examples of that in a moment, but we can do similar things in tracking problems where we're now looking at an object moving spatially, and perhaps its x and y position if it's a two-dimensional problem, and we can now think of parameterizing times at which, random times tau k, at which the object changes its maneuver characteristics. For example, moving from a left turn to a right turn, to a stronger right turn, to almost straight on, this kind of thing. So each maneuver will have its own parameter that needs to be estimated that tells you the characteristics of where it's heading next, and also the time of arrival, the change point time at which that new parameter switches in. And a lot of these models we use actually in a deterministic fashion, so that the path is that these are piecewise deterministic processes that we're estimating. There's quite a lot of theory about those, of course, where you have random times of arrival of a new parameter, but then given that parameter, the path to the next point is then a deterministic path. In contrast with the OU process model that I just described for the finance data, which has random components, it's a random stochastic process in between change points as well. And to do the inference, well, we need to assume some model for the noise. Well, let's be very simple about that and say that the noise appears as the unobserved state variable at the observation time ti plus some Gaussian noise component. That's people in finance will know that that's a big approximation to the kind of market microstructure effects that actually occur, but it certainly absorbs randomness, which can be on an appropriate scale for what's seen in the actual data. And we want to do sequential inference for this, so we'll see a string of these observations arriving at times t of I, which are not generally related to the jump times tau of k. And we want to sequentially infer the unknown jump times from the data, and we're using a Monte Carlo particle filter, a sequential MCMC approach to implement the Bayesian recursive update formulae. And the likelihoods in our finance model, because we have a Gaussian transition density conditioned upon the change point times, the jump times tau of k, can be computed very simply actually using a Kalman filter, which gives you a sequential output of the likelihood for each sequence of possible change points that are investigated within the Monte Carlo algorithm. So the Monte Carlo is basically, putting it simply, is just throwing out a whole sequence of possible trajectories for the positions of the jump times and weighting them according to their likelihoods, and then resampling with replacement according to those likelihoods. So that's a very simple bootstrap type version of the Markov chain of the particle filter method. And this is all done within a state space formulation, and as I say, using sequential Monte Carlo. Now I may want to skip over a little bit here. Essentially, I was just going to, I don't need to say this probably for this audience, but we're looking at state space models with a hidden state x, modeling this hidden state behavior over time, and then some likelihood function that models the sensor or the measurement in terms of the hidden state. And typically a Markov structure for that, the hidden states evolve through time according to their transition densities, and we're not going to go through all that stuff either. And the observations hang off those hidden states through some specified observation density. So the Monte Carlo filtering task then says, I've used a notation alpha for my latent state variable here. That's the same as the x from the previous slides. If I look at if I have my posterior inference, for all of the states up to time t, given all of the data z replaces y on this slide, apologies for that, then I want to do the sequential inference just like for a Kalman filter to input a new data point and have a new posterior distribution for all the hidden states given all of the new data. And we could do that using the standard Bayesian filtering update formulae in a sort of a smoothing formulation that includes all of the past history as well. So we do the basically just do the forward prediction one step based on our previous solution times the transition density to the new state, and then the update step using Bayes' theorem to get you to the new result. So the sequential Monte Carlo are just a Monte Carlo realization of this sequential updating for all the states through time. And we represent in the Monte Carlo at each time a sequence of trajectories for the states, the posterior distribution for all the hidden states given all of the data up to the current time, in terms of here an unweighted set of Dirac point masses sitting at the random sampled trajectories that are coming out of the filter sequentially through time. And then we just plug that into the prediction and correction equations, just like for the Kalman filter, but here with a Monte Carlo representation, and that then is the updated target distribution. And we tend to update these using importance sampling from this target distribution with a discrete support for the past trajectories and a continuous, generally continuous support for the new bit of the trajectory that gets added on at time t+1. Okay, I shan't go into any more details of that here, but for the jump models that I talked about, things are similar, but of course the alpha process occurs on an irregular time axis with a new state appearing for whenever a new tau is generated. But it can be, the basic particle filter, sequential Monte Carlo, can be adapted in a similar way to this framework with the jumps. And that, with a few twiddles and extra bells and whistles, that's what we do. It basically takes, for a tracking example here, you assume you've filtered up to, you have a number of random samples labeled 1 through n. Each sample is an entire trajectory of the hidden state, including the arrival times of the jumps and the parameters of all the jumps or change points. And at time t, you basically continually draw new jump times and append them to the old jump times from the transition density until such time as your next jump has gone into the future. So basically, you just extend the continuous time skeleton of the underlying hidden state process for each random sample, for each random trajectory, and wait till it's extended into the future, and then evaluate a weight for that in terms of the incremental likelihood function for the new observation, given all the old observations and the particle trajectory. And then you can resample that and then proceed to the next step. There are plenty of tricks and better ways of doing this, but that's just the kind of vanilla basic implementation of the scheme. If you run that on a tracking example, you can see what's happening here. What I'm doing here is there's a ship moving, and there are a number of sharp changes to its trajectory. So we model these with one of the, these jump processes. So the parameters are supposed to change at all of these sudden change locations along the trajectory. Well, the particle filter is presented, though, with cluttered observations. So all of these cyan dots show all of the observations that you receive at one single time, one or more of which, a few of which might refer to the actual object position, which is sitting somewhere in the middle here. So it has to disambiguate a whole load of clutter from some genuine object information which appears occasionally in the middle there. And it does this over time quite successfully. And what you see here after a few time steps are all of the trajectories that the particle filter randomly threw out, the ones that are all being entertained after, I think, the first 10 time steps of the algorithm. So it threw out from an initialization somewhere in here a lot of possibilities that are all consistent with the data. And then it gradually prunes those away at each time step by the resampling operation, which is this sampling with replacement according to the weights calculated by the likelihood. And so what we should see, this is a video, should be a lot more of these trajectories being sequentially generated through time, most of them being pruned away and thrown out because they're not consistent with the data, but a whole lot of hypotheses being entertained as it tracks around this data. See if this will actually play. So here you see it running. And it's following the trajectory plus a whole load of other hypotheses that are still consistent with the data. Because the data is so ambiguous that you simply cannot tell until you have a retrospective look of quite a few data points in the future which ones of these need to be thrown away. And the algorithm needs to have a sufficient variability in its parameters that it can model very sharp sudden turns to the left or right. And you just don't know whether those have happened until a number of time points have occurred into the future. So you can see what happens there. You basically get all of these blue trajectories are the ones that are left at the end of the run. It's not very accurate at the start, but it's because the data is so noisy and ambiguous, but it's certainly able to track the general path of the object and maintaining a good degree of uncertainty, probabilistic uncertainty, as you would wish. There are better ways of doing this. So our recent work, for example, working on the finance data, is looking at some retrospective smoothing algorithms applied to these types of change point jump models. We call them variable rate models. So if you apply this kind of jump estimation to the to a finance example, again, this is an exchange rate data series over time, and if we apply just the filtering, which was what I showed you in that previous slide for a tracking example, you basically get, now let's see, what are we looking at? We're monitoring here the x dot process, the slope process of this, so it's finding some fairly clear jumps at reasonably plausible places in the time derivative of this function here. It's not quite clear. There's a lot of ambiguity in the data. But there's not much diversity in what's coming out of the particle filter, except for the front end, where it's able to maintain quite a lot of probabilistic uncertainty. So the algorithm here is probably not working that well. It's basically getting stuck on a few plausible trajectories for the process. But do we really believe that those confidence bounds should be that tight? I don't think we do. And similarly, you can plot things like probability distributions for where jumps are occurring in the price process itself and in the slope process. And it's giving some plausible inferences. I can't remember what the color coding is there, but it's basically some kind of jump is occurring wherever there's a peak there. And more recent work is doing retrospective backward smoothing with these models, where you take your filter output, and at each time step, potentially, you can do a backwards smoothing pass, just like you do with a Kalman smoother, but here operating with these different models and in a somewhat non-Gaussian environment. And now you start to see the algorithm is able to pull out a much more reasonable probabilistic posterior distribution, the uncertainty about the value of the slope process right back to the time origin where we initialized back here. And similarly, you're able to get reasonable probabilities for where the jumps of the different types have occurred, with much more, we believe, more meaningful values than you get from the straightforward filtering. So that's fairly recent work. Just want to briefly touch on this topic of jumps taken to the nth degree. So what I've talked about there previously was where you have obviously finite numbers of jumps, almost surely, within any finite time interval. But actually, for a lot of processes, it's perhaps more realistic to say that, that there are jumps occurring all the time. And there's perhaps an infinite collection of large, small, tiny jumps occurring in each finite time interval. Could one possibly deal with a scenario like that? So one way you can deal with that is using a non-Gaussian Levy process, and perhaps the most natural way to extend the Brownian case is to use the alpha-stable Levy process. So this is a very heavy-tailed type of Levy process, another continuous time stochastic process, and it has a theoretical justification in many areas that relate to my work in communications, where you have lots of random sources all combining to interfere at any given time, and signal processing and finance, debatably, and not everyone thinks it's suitable for finance. And we can extend the kind of filtering and inference ideas that I talked about into this framework using some very powerful representations based on these processes. That's pretty well saying exactly what I already said. Stable distributions are just a family of probability distributions that model very heavy tail behavior down to the Gaussian in a limiting case, and they have several parameters which you might want to estimate automatically from the data, and it's that we're targeting here. Can one actually infer that from the data? And the way we're doing this, well, pose it in terms of again a Levy process, so we can do the stochastic integration in principle to get the value of the process at time t at some starting origin x of naught. And now, excuse me, Now we'd like to replace the Brownian motion again, instead of with the jump process with change points, with one of these alpha stable Levy processes. And these are processes which have independent increments, but almost surely an infinite number of jumps in finite time intervals. And if we look at the difference between two times for the process, those are distributed according to one of these alpha stable distributions with its parameters alpha for the tail thickness and beta for the skewness, and the scale parameter depending on the time difference between the 2 points. These are generally highly intractable for inference, and you can see the kind of behaviors you get. Here's Brownian motion on the left, and here's a alpha 1.5 process able to exhibit quite large jumps occasionally and then small jumps most of the time along time. And there are various ways for doing inference for these, but nothing satisfactory that we're aware of for continuous time processes with these alpha stable Levy processes driving them. Certainly nothing that gives you a fully Bayesian inference about the parameters and the state of such a system. So, to cut a very long story short, we're doing this, replacing inference directly for the alpha stable distributions using this powerful representation for alternative representation for them. So each alpha stable random variable in the process can be represented as an infinite summation of random variables. And I shan't go into the details of these, but basically what we're going to do is we're going to make all of these random variables part of the Monte Carlo inference scheme and try and infer them. And it actually sounds rather unpromising, I know, but it actually lands us back into a conditionally Gaussian framework where you can go and evaluate likelihoods again using Kalman filters exactly as before. So I shan't go into the details of that, other than to say this does have an physical interpretation in terms of jumps of a process. Basically, you can think of this as an infinite sequence of jumps, just like for the finite jump case, each given by a random size composed of two random variables multiplied together. And these occur at uniformly distributed random times, and there's an infinite number of them. So there's a whole series of these of decreasing size at random times uniformly in your time interval. And basically, and we don't need the next slide, that's just the formal result for the stochastic process. And I'm going to skip forward now and just show you that the result we get is that conditional on these random variables, these gammas of I that I talked about relating to the size of the jumps, we can write the whole process as a conditionally normal process, conditional on the parameters of the alpha stable model, these mu's and sigmas and latent variables gamma. And that means that the whole thing can be plugged back into a filtering or Bayesian inference framework quite nicely with a lot of auxiliary variables, latent variables that have to be sampled, just like the jump times were sampled in the finite number of jumps case. Okay, I shan't go into any details there. The rest of it is about trickery for how you would actually construct a sampler to meaningfully get output from these models, and that is a big chunk of work. But suffice it to say that it does actually give some nice results. So you can get things like Bayesian inference for the tail thickness parameter from rather short data sets of only a few hundred data points. So this should have been 0.5, and this is giving us a rather nice posterior inference about that parameter with no prior information other than a uniform prior on alpha specified. And similarly, the other parameters of the model pop out with their own posterior distributions, obtained this time using a Markov chain Monte Carlo rather than a sequential Monte Carlo approach. And we need that. We can easily incorporate them into time series state space models. So here, for example, we plug them in as the driving noise for an autoregressive model, not a time-varying autoregressive model as we've heard about in other talks in the conference, but a time constant one, but driven by one of these alpha stable processes. Now, this hasn't popped out very well, but this is showing the algorithm as it proceeds with its iteration number in the Markov chain Monte Carlo approach, basically approaching the true values of the parameters and operating with a highly non-Gaussian asymmetric driving noise. And here you can also do model order selection, so you can incorporate this into a Bayesian model choice scenario. So here we have lots of different initializations, and they're all converging with high certainty to the correct model order for this synthetically generated autoregressive data sequence. And so again, that's with iteration number of the Markov chain algorithm, and this is time for the time series as plotted. That's a resonant fifth order autoregressive model driven by one of these alpha stable noise processes. And we can do state estimation for continuous time models. As I said, that's really where we're heading with this work. So we're looking at things here, for example, for a continuous time autoregression, first order, driven by an alpha stable Levy process, so the continuous time versions of these things. That's looking promising as well. And I think I'm going to wind up there, other than just to say that this last topic that I won't have time to talk about is the one where we're looking at change points in group structures of objects. So maybe I can just flick towards a couple of slides to show you what's going on. You have objects moving around spatially. You want to work out their positions over time, but also how they relate to each other. So here, to the eye, it looks like we have three distinct groups of objects. Can we automatically learn that from their behavior over time, their kinetic behavior? And can we detect change points where the group structure changes, where perhaps one object joins another group, or a group splits in two, this kind of thing. So that's the sort of situational awareness inference that we're trying to do there. Like we'd like to split it up into three groups like that. Now, I shan't go into the details of this, just no time, but basically, by making a coordinated continuous time stochastic process model for members of the same group over time, just ignore this, we can get a coordinated behavior for single groups of objects. For example, four objects. This is supposed to be an aircraft flight moving through time. And we can infer this using sequential Monte Carlo algorithms. And just to conclude with a very simple example, the types of things it does in detecting a change point. Here's an example where you have four objects moving spatially, x, y coordinates. They start off as two pairs of objects moving in. Each pair is coordinated with itself, with its partner, and but independently moving. And then they join together in a single group in a single coordinated motion. Can we detect that automatically online as a change point? Well, the data that you see would be like this. So again, it's a cluttered tracking problem. So most of the stuff you see will be just random points uniformly drawn from a Poisson process. But occasionally, some of the points will correspond to correct observations from the objects, the four objects that are moving spatially, starting in the top left and top right-hand corners of the scene. So that, if we look at the data, a lot of random stuff. You can't really see where the objects are. They're moving here and here. At some point, it becomes a little clearer. Now you can start to perhaps see a cluster of correct measurements coming down here. There are plenty of mismeasurements again, so in plenty of frames, you don't even see the objects you're trying to track at all, but they appear in some frames with a certain probability, again, according to a Poisson point process model. And if you set that as the inference task, then you get this type of output. So here's after, in the second time step, where it's detected initially some activity up in the top left, a couple of pieces of activity in the top right, and we'd now like to see whether it can classify over time what the grouping structure, what the interaction structure is for those objects. So if we run that again as a video, yeah. We can see now the Monte Carlo algorithm is giving us a sort of object density map for where the things are. So now it's pulled out of that data that there are four objects, shown by these sort of kernel densities proceeding through time, and they appear to be grouped together. If you look here, I've enumerated for this small problem all of the possible groupings for those four objects. And we look at the posterior probabilities coming out for the algorithms. And this one here, for the first half, is for two separate groups of two objects. And at this point, this is where the four objects join together as one group and move vertically down here, and then it's clearly found with very high probability lighting up here that there's just one group of four. So it sort of picks up these change points in the dynamic structure of the groups as a very latent variable in the setup in the system. And that is all I have time for. I'm not going to say any more. I hope this hasn't been too off track for the workshop, and it gives a flavour of some of the older work and ongoing work that we're doing in these change point related areas. That's it.
Are you familiar with the work of Lai and Singh? That resembles this to some extent. I think the details are different, but it's basically
Which bit?
the first part.
The first part, on they applying it to finance data.
They're interested in finance.
We may have that in our reference list. I'll have a look. Are they using jump diffusion models for?
No, they're using discrete models, but they're filtering the data. They're assuming that at a rather sparse set of observations, there's a change. They assume that you have a geometric prior between changes with a small p, so that changes take place far apart.
Right, yes.
And I think the model is that each time a change occurs, the mean value of future observations gets a new value. I think it's a new value independent, not accumulated.
I see. Yes. Okay. Oh no, I'd have to have a look at that.
And then they write down the filtering equations and try to do something with it.
Yeah. Okay. Yeah. We may have it. There's a huge literature on all these processes.
I'm sure. I know one of their goals, which might or might not be relevant to what you're doing as well, was to show that at a point when there was a lot of discussion about how long-term dependent models are required for modeling financial markets, to show that if you allowed these jumps, if you allowed change points, then you didn't need long-range dependence. You could use Markovian type.
Yes, absolutely. Yeah, that's a rather nice conclusion. And there's a bit of discussion can be had about whether clusters of jumps can be used as a proxy for stochastic volatility, which people use a lot in finance. There are some interesting things to be sorted out there. Yeah. Thank you.
Can I have a technical question? I'm wondering, how can you avoid, in your first part of your presentation, how can you avoid particle degeneracy in your sequential Monte Carlo methods?
I showed you that you do get particle degeneracy if you look at very long histories on the trajectories. I mean, these things are usually run. If it's a well-constructed filter, they usually run okay for the filtering density, learning things at the front end of the data, and then they get progressively more degenerate as you look retrospectively back from the current time. And that does happen with these filters. Inevitably, it does. But if there's enough kind of noise in the system, then it sort of sorts itself out and works okay. With the backwards smoothing, you can enhance the performance quite a lot, even retrospectively. So you're able to effectively rejuvenate the paths from the very degenerate stuff that you see from a pure filter with the backwards smoothing and sampling. Yeah. So I mean, I know none of these methods is perfect, and you can get degeneracy, which means that it just degenerates down to one or a few paths rather than a full proper Monte Carlo representation of a density. In which case you've sort of lost track or lost the game, really. But yeah, it could occasionally happen.
If there's no more questions, that we thank again.